In the preceding discussion, we learned how to take an arbitrary quadratic, ax squared plus bx plus c, and how, using the transformation of completing the square, to rewrite it into something called the standard form, which is given here, a times x minus h squared plus k. So what's that standard form good for? Suppose that we know how to graph the function y equals x squared. That's the simplest possible parabola, right? So there's no linear term and no constant term. That's as simple as parabolas get. So suppose we know how to plot it, but for some reason we have forgotten or we do not know how to plot any other quadratic function. So could we use the standard form of an arbitrary quadratic function to relate its graph to the graph of the most simple parabola, that of y equals x squared? So can we use the standard form of an arbitrary quadratic to relate the graph of a times x plus h squared plus k to this well-known graph of y equals x squared? So can we relate the graph of this guy to the graph of y equals x squared? Okay, so let's see how that's done using the standard form of our quadratic. First, we notice that if we want to get from x squared to the standard form of a times x minus h squared plus k, what we need to do is we need to take the function x squared and transform it to the function a times x squared. Now, here, with the gray color, I have the original function x squared, and with the red color here, I'm having the function a times x squared. So multiplying x squared by the number a corresponds to stretching the graph of x squared by a factor of a. That's if a is positive. If a is negative, you also need to reflect across the x-axis. Next, in order to go from ax squared to the standard form of our quadratic, I need to replace ax squared with the expression a times x minus h squared. So I'm replacing the argument x with the argument x minus h. As we know from previous discussions, replacing its argument by argument minus a given quantity corresponds to translating the graph of that function by the quantity that you see here. So if I have replaced x with x minus h, I have translated the graph of my function h units. And finally, if I want to get from the function a times x minus h squared to the function a times x minus h squared plus k, all I need to do is I need to add k units, which corresponds to shifting the graph of the intermediate function with k units. And so finally, I started with y equals x squared. So I started with y equals x squared. That was this function. Then I transformed it to y equals a times x squared. So I squished my function in the vertical direction. Then I translated the graph of my function to the graph of a times x minus h squared, and finally I translate it again, shifting down k units, a times x minus h squared plus k. So this standard form shows us how to transition from the graph of y equals x squared to the graph of an arbitrary quadratic. That is why all quadratic functions look pretty much like the graph of the function y equals x squared, but with different steepness and with different position of this vertex point, of this tip point, of this bottom of a cup. So when the leading coefficient A is positive, the parabola opens upwards. So we're having a cup which opens in the vertical direction. Mind you that this cup opens infinitely wide, yet its sides tend to be very, very steep as x tends to infinity. So that's a kind of a weird type of cup. Now, when the leading coefficient A is negative, our parabola opens downwards. So we're having an upside down cup. When the absolute value of the parameter A increases, the parabola becomes steeper. So if I'm to take the number A and make it larger in absolute value, my parabola is steeper. And if A is positive, my cup has more vertical walls. This special point is called the vertex of the parabola. That's the lowest point on the parabola if the parabola opens up, or the highest point of the parabola if the parabola opens down. So that point, as we illustrated, its coordinates are h and k. These are the numbers which we obtain by completing the square. The number h is equal to minus b over 2a, and the number k, we found it, that's minus the discriminant over 4a. Our discussion also showed the careful student that the graph of our quadratic function is symmetric across the line passing through x equal to h. So that graph of that quadratic function is symmetric across the line x equals h, because the original simple parabola y equals x squared was symmetric across the y-axis. Symmetric, what does it mean for the graph of the function to be symmetric across the line? That means that if I take a point on the function, I drop a perpendicular towards the line, and then I extend it on the other side of the line so that this distance here equals that distance, then I'm going to land at a point on the graph of that function. So once again, if I start on the graph of the function, I drop a perpendicular to the line, go on the other side, marking the same distance as on the right hand side, then I still obtain a point on the same graph, the same function. So when we move the numbers h and k, when we change the numbers h and k, we simply are changing the vertex of our parabola, right? So the vertex of our parabola is given by numbers h and k. And so when we change them, we're just moving the vertex of the parabola around, okay? But notice that the numbers h and k, they do not affect the steepness of our parabola. So if I were to change numbers h and k, I don't affect the steepness of my parabola, which means that if I change the number b and I change the number c in the expression ax squared plus bx plus c, I do not change the steepness. So the steepness of a parabola depends entirely on the leading coefficient